Okay. So everyone should have gotten an email about the course evaluations to fill out. Those are being handled in another office. So they'll end up going to Todd Bruce, Dr. Bruce's husband, who's in charge of that, and so he'll take care of it, and then he'll send the faculty the evaluations after all the grades are turned in. So normally the faculty would be in charge of collecting their own, so that's not happening. So I would encourage you to fill those out. This is your opportunity to give official feedback on the class, what you found effective, what you didn't find effective. If you have any suggestions, I will take those under consideration for next semester. This is your opportunity to basically assess that, just like I have an obligation to assess you with a grade. So this is your official opportunity to do that. There's many unofficial ways that you could do that if Rate My Professor is still in business, although they're chili pepperless now. I think that's a Me Too thing. They took away the chili peppers. I had none, so didn't lose anything. I have not looked at Rate My Professor for years, so it's not really official. But course evaluations are. So, and to provide incentive if you already haven't turned one in, what I will do is I will drop your lowest homework at the end of the chapter homework score. So in order for me to know that you turned one in, when you turn it in, you should get an email receipt that says you did that. Just forward that email on to me. It just tells me that you filled it out. In the past, I would have said whether you filled one out all blanks or with things. Then I just saw a check mark in the box that said, hey, you filled one out. Didn't see what the results were. So if you forward on your receipt that you filled one out, then I will drop the lowest quiz. No, I'll drop the lowest homework problem score in the 12 chapters. Now, that does not mean that you should just then not do chapter 12 because you can drop it. It means that I'll drop the lowest score. Okay. And that's just to provide some incentive. And then I'll build that into the syllabus next semester, because I know that that's what I'll be doing. Final exam is next Friday at 8 a.m. in this room. So it will be multiple choice. It will be similar but not exact to some of the problems that are in the practice problem set at the end in the last folder. So I would strongly encourage you to do those. I release the answer key at the end of class on Wednesday. And if you had any questions about those, feel free to email me or come and see me. I will be available over the weekend in the afternoon. I'll be in doing whatever it is I need to do. So if you had any questions and wanted to stop by, I'll leave the door open so that, can't guarantee morning, can't guarantee after 5, but I'll be in the afternoons. So, and I'll be in all next week too. I think I only have one set of meetings on Tuesday afternoon, and then the big holiday soiree on Thursday afternoon, which I probably won't be going to. So I'll pass on Big Shrimp. This is their bonus for us, which is better than nothing, I guess. So the exam will be multiple choice, and it'll cover pretty much everything. I will try to put together some extra naming practice problems. If you didn't get a chance to do the naming practice problems that I had given out before the first exam, it'd be a good time to do that one too. You will get the sheet. You'll get the sheet that lists the naming priorities. So you'll still get that sheet. You'll get a periodic table. So you will get that information. So you just have to know how to use it. And it may have been a while, so you can do that. Okay. So is there any questions about?
The two lowest scores being dropped, or just the one?
I think in the syllabus it says the lowest two, right? So since there were only 4 things in that, which will change for next semester, there'll be a lot more, then the two lowest will still be dropped. That's actually normally what I give people credit for filling out the evaluation is a 3rd drop. But if I give people a 3rd drop, then everybody gets 100%. And I figure you might need the lower drop on the chapter problems. So, and at the end, when all's said and done and I have all the scores, that's when I do, if I'm going to do a little bit of curving, I will curve down, starting with the percentage that's in the syllabus and going down from there. So I have provided a little bit of curve on exam 2 and 3, but there'll probably be a little bit to take into account exam 1. But I won't know until the end. So for those of you who are like, what do I need? I don't know what you need. You could go on Canvas and you could use, like, they have a what if function or something. But my suggestion is do the best you can, get the highest score you can, and push as high as you can get. Because, if you're like, oh, all I need, I mean, that's like playing prevent defense in football. And I don't know, but that usually doesn't work very well. Doesn't work well for the Browns, but So you want to just try and do the best you can. And prepare the best you can, given all of the other stuff that you've got. And if you have questions, email me, come see me, because I will be in all week. Okay, so we have a couple of things to finish up, and then I'd be more than willing to answer any questions that you have. So last time we were talking about epoxides. And epoxides, the good thing about epoxides is that they are a review for the bromonium ion and the mercuration-demercuration reaction. So what we said on Wednesday was, let's take and add an acid to the epoxide. And so when we add an acid to the epoxide, we're going to protonate the oxygen. And when we protonate that epoxide, it now looks like a bromonium ion or the mercurium ion. And so the oxygen with the plus charge, it doesn't really want the plus charge, so it's going to push that positive charge down to the carbons so that those carbons then share the positive charge. And the carbon on the left is going to have more delta positive charge because it's more substituted. So whenever we protonate, whatever the nucleophile is next is always going to add to the more substituted carbon. So if we protonate this, we force then, if for instance I added H plus Br minus to this, the Br minus would then be forced to come in and add to the carbon with the most delta positive charge. So that when that happens, the OH group then swings over to the right. The bromine has now added trans to the OH, but the bromine is now added to the carbon with the most substituents, and the OH then ends up on the carbon with the most hydrogens. Okay. It's not appropriate to use Markovnikov and anti-Markovnikov for these reactions because we're not adding anything to a double bond, which is where Markovnikov and anti-Markovnikov are. But if I think about where the epoxide came from, the epoxide came from a double bond. Whether I reacted the epoxide with our peroxy acid to make it directly, or whether I made a bromohydrin out of it, I can think about the final product in terms of what was essentially added to this double bond to begin with, even though it wasn't added in one step. So for instance, if I said, I'm going to add Br2 and water to that double bond, what would the product be? So what group goes on the left carbon? What group goes on the right carbon? Ashton?
The left carbon gets the OH and the right carbon gets the...
Okay, so Br2 and water. What am I adding? Br, OH. How? If I treat the Br as if it was an H+, Markovnikov. 100% trans. So that would be the product if I took the double bond and I added Br2 and water to it. I've added the OH to the carbon with the two methyls and the Br there. So one of the reasons why we talk about epoxides now is because look at the product that I made after I made the epoxide and added HBr to it. I made the exact opposite. The Br is now on the carbon with the most alkyl groups, and the OH is now on the carbon with the most hydrogens. So the reason that epoxides are important is because they allow us to form the opposite products that we can if we just do a one-step reaction directly with the double bond. If you convert it into an epoxide, you can now do other reactions that you couldn't do with a direct double bond. So this is one example. Making the epoxide and adding H plus Br or HBr gives you the opposite of what you would get with the bromonium ion. And there are others. If we take our epoxide and we add H plus H2O to it, which is what we did last time, I'm going to protonate the epoxide, oxygen, the water is going to add to the carbon on the left. I'm going to end up with an oxonium ion. So the OH then slides over to the right. And then I'm going to lose the H plus. So that I now added the two OHs trans, 100% trans. And what did we talk about on Wednesday? Again, starting with a double bond. We can again convert that to the epoxide. So if I wanted to add two OH groups trans, what I should do is make the epoxide and add it with H plus H2O. If I wanted to add the two OHs cis, what should I do? What reagent should I use? Starts with K. KMNO4 and KMNO4 and, since we're adding OHs, KMNO4 and base. KMNO4 and base. So I can add the OHs cis, I can add the OHs trans. It just depends on whether I want to do it in one step, and if I want trans, I can't do it in one step. I need to make the epoxide and then what's called open up the epoxide by using acid and water. So whenever you use acid, you're going to get the nucleophile adding to the carbon that's most substituted. So that's why we use epoxides, because it gives us this ability to do one reaction and then change it and do another reaction. So the BR and the OH, I can add them both ways now. The OHs, I can add both cis and trans. So is everybody okay with this?
What did you say the difference was between adding an acid and base versus the acid?
I didn't say anything about a base yet. But when you add acid, the nucleophile that's with the acid, like water or the Br minus, always adds to the carbon that's most substituted, because that's the carbon with the greatest delta positive charge. Right. And we'll talk about, I don't remember if the book has the epoxide without acid, but normally we talk about that at the beginning of next semester. What happens there? Okay. All right, so everybody okay? Last topic for this semester. Oxidative cleavage. So let's take these two words. Usually our reactions are pretty descriptive, right? Cis hydroxylation means we're adding two OHs cis. When we talked about hydrogenation, that means we're adding H2 to a double bond. So what does oxidative cleavage mean? Oxidative cleavage means that when you have a double bond, we are going to add oxygens to each carbon. That's the oxidative part. And we are going to break the double bond, which is the cleavage part. So there's several reagents we can use to do this. So let's start with KMNO4 and now acid. So KMNO4 and base adds two OHs. And that's how I suggest, maybe you remember it is, KMNO4 and hydroxide adds two hydroxides. That's cis hydroxylation. KMNO4 and acid cleaves. This is a harsher set of conditions. And so what it's going to do is it's going to cleave the double bond. So the way we write the product here is we basically come over here and we erase the double bond. And what's going to go in the double bond's place? A double bonded oxygen. So we cleave the double bond and then add a double bonded oxygen to each carbon. And that's it, sort of. Now we have to think about what each of these two carbonyls is. And there's only two choices. Well, there's three choices. These carbonyls could have one alkyl group and a hydrogen. They could have two alkyl groups, or they could have two hydrogens. Because in our original alkene, those are our choices. Each carbon can either have one or two alkyl groups or one or two hydrogens. So this is an aldehyde. This is a ketone. And this is 4-maldehyde. Which is the 1-carbon aldehyde. Okay. So the question is, after I cleave the double bond and I convert each carbon into a carbonyl, the question is, which one of these could further react with KMNO4 and acid? Okay. Because I'm always using excess KMNO4. So this is always in excess, and so the problem there becomes, okay, can that excess KMNO4 react with any of the products that I just made? And if they do, then those products get further oxidized to their final products. So what we should talk about is, we should sort of talk about the oxidation reduction scheme that involves aldehydes. So if I start with a primary alcohol, okay, why is this a primary alcohol? Because the OH is attached to a carbon that's primary. I can oxidize this to an aldehyde. And if you're saying, well, where's the oxidation? Because it didn't gain any more oxygens, it didn't. It lost two hydrogens. So this loses 2 hydrogens to get to the aldehyde. And then you can further oxidize an aldehyde. Whoops. Further oxidize it with the O in brackets to a carboxylic acid. And that's as far as it goes. So the oxidation scheme, and if I reverse this, the reduction scheme, is primary alcohol to aldehyde to carboxylic acid. And carboxylic acid is as high as it's going to be oxidized. Okay, and CaMnO4, hydrogen peroxide, and there are other reagents that will do this. They will convert the primary alcohol all the way up to the carboxylic acid. Now what we're interested in is what reagents will do this conversion. What reagents will convert an aldehyde to a carboxylic acid, and they are CaMnO4 and H2O2. And you might say, well, H2O2, it's in our next reaction. So whenever I'm using CaMnO4 to do cleavage, if I over here create an aldehyde, that aldehyde, the excess CaMnO4 will react with, and it will convert it to a carboxylic acid. So when we erase the double bond and we can make our carbonyls, we have to check, because if any of those are aldehydes, they will be further oxidized to a carboxylic acid. So the final answer for that piece is the carboxylic acid. Now, this formaldehyde piece is important because it would occur if the double bond was at the end of the chain. So if you have a double bond that's the end of the chain, which is sometimes called a terminal alkene, that has a CH2 at the end of it. What would happen to CH2, or what would happen to formaldehyde? Well, first of all, if you've heard of formaldehyde, it's usually what dead things are in, right? Like the dead frogs and other things in biology, except I don't think they use formaldehyde. I think they use methanol now, because formaldehyde's a tad bit toxic. So sometimes you'll hear about people make, there's products that you put in your home that might have formaldehyde, and so you have to test and make sure that it's not, that the gas isn't coming out. But formaldehyde is actually a gas. When you dissolve it in water, you make formalin, which is what you put the dead things in. So formaldehyde, when it's oxidized to this acid. Which is called carbonic acid. So CaMnO4 will oxidize. CaMnO4 and hydrogen peroxide will oxidize formaldehyde to carbonic acid. But carbonic acid isn't really stable. If it was a little bit later in the day, I would reach over and I would say, I'm going to drink some carbonic acid. This is coffee, no carbonic acid in it. Because I don't think they make fizzy coffee. They don't make fizzy coffee yet. Right? We make it all sorts of foo-foo ways, but we don't have fizzy coffee yet. If we had fizzy coffee, it would have carbonic acid in it. So that means carbonic acid decomposes into what? CO2 and water. And that's going to be the final product then. So if we make formaldehyde in our cleavage, it's going to be further oxidized up to CO2 and water. And you might say, yeah, who cares? Well, couple reason to care about this. Next semester in lab, we're going to spend a number of weeks talking about how we determine structures of molecules. Because so far we've just kind of written our products down, but in the lab, if we do a reaction, how do we really know that we made that compound? So we're going to be talking about a lot of different spectroscopic techniques. Infrared, NMR, mass spec. But in the old days before they had those instruments, they had to determine what the structure of the molecule was. So they had all these qualitative tests. For instance, I think I have a double bond. Okay? If I think I have a double bond, what I'm going to do is I'm going to take bromine, which is red, put a drop of bromine in my compound. If it's a double bond, it's going to add 2 BRs, 100% trans, and the orange color is going to disappear immediately. So that can tell me that I have a double bond. If I think that double bond is at the end of the chain, I'll do KMNO4 oxidation and I will look for the fizz. And if I see the reaction discharge CO2 by fizzing, then the double bond's at the end of the chain. If it doesn't, then the double bond's inside the chain. So you had to do all these little color tests to try and figure out what your structure was. And we'll actually be doing some of those in lab. You'll be making an ester and you don't know what the structure is. So we'll do some of those tests to try and figure out what it is. So that's the importance of this whole process, is that it can be used to determine whether the double bond is at the end or the middle of the compound. Now, the book problems, they're going to give you the products of the oxidation, and then you got to figure out how to piece them back together again, which is kind of a backwards thinking. But let's get to that in a moment. So that's what we do. We cleave the double bond, we make them carbonyls, and then anything that's an aldehyde or formaldehyde gets oxidized up to the carboxylic acid or CO2 and H2O. So let's do a reaction. Let's do an acyclic one. Okay, so here's a double bond, and I'm going to add KMNO4 acid to it. Okay, so can we write the products of this reaction? First thing I'm going to do is I'm going to write my two molecules without the double bond and convert them into carbonyls. And I do it this way just because I'm mimicking that I'm erasing the double bond and putting two O's, two double bond oxygens in. Now this ketone, which is acetone, nothing happens to it. This, in the presence of KMNO4, is going to do what? It's going to be oxidized to a carboxylic acid. So these two products, those are going to be my major products of that reaction. The 2-carbon acid, which is called acetic acid, and acetone. What happens in the case of a ring? Same thing. I'm going to erase the double bond in the ring. And make each of the carbons carbonyls. The carbonyl at the bottom has a hydrogen on it because over here I had a hydrogen. So when you actually cleave a ring, you only get one molecule. Because while you cleave that double bond, the rest of the ring is holding it together. Okay. So did I make an aldehyde? Did I need to react with KMNO4? Yes. So this is going to be oxidized to a carboxylic acid. So this would be my final product. And if I have to unwind that molecule and draw it straight across horizontally so that I don't lose anything, what I like to do is I like to start at the beginning and say, oh, that's going to be carbon 1, 2, 3, 4, 5, 6, and 7. This isn't IUPAC numbering, this is just numbering for me. And so I'd say, okay, carbon 1 is going to be a CH3, carbon 2 is my carbonyl, then I've got carbon 3 is a CH2, carbon 4 is a CH2, carbon 5 is a CH2, carbon 6 is a CH2, and then I've got my carbonyl of 7, and then my OH. So if I want to write the structure horizontally, when you're first starting, I strongly encourage you to number them so that way it makes it easier to unstretch the molecule. And you don't gain any carbons or you don't lose any carbons. So the product could be written either way. So that's cleavage. Erase the double bond, any aldehydes get oxidized up with KMNO4 and H+. Everybody okay? All right. Last two reactions then. There's another way to do this which is more traditional. The more traditional way of doing this is what's called ozonolysis. So ozonolysis is another way to do this reaction. And ozonolysis gives us a choice. Do I want to oxidize that aldehyde or do I not want to oxidize that aldehyde? With KMNO4 and acid, I have no choice. KMNO4 is going to oxidize the aldehyde. But in ozonolysis, I can choose my reagent to either oxidize or not oxidize. So lysis means cleave, right? You lyse cells. So we're cleaving with ozone. And what's ozone? Ozone is O3. So if I take my same if I take this aldehyde and I treat it with ozone, with O3, it's going to do the cleavage. So that means I'm going to get this carbonyl and I'm going to use two different reagents, so I'm going to write this twice. So again, I'm just erasing the double bond, throwing in a C double bond O. But ozone can go with two different reagents. The first reagent is if I use ozone and hydrogen peroxide. It's going to do exactly what KMNO4 and acid did. That's why I said aldehydes plus KMNO4 or aldehydes plus peroxide. This is going to be converted to the carboxylic acid. So if we do ozonolysis with hydrogen peroxide, we're going to get ketones and carboxylic acids. Bless you. So if I want to do that reaction, I'll go ahead and use ozone and peroxide. What if I don't want to do that? What if I want to keep these two molecules exactly the same? Well, then we could use, and my favorite is, we can use ozone with R2S. R2S is the sulfur equivalent of an ether. And so if I use ozone and R2S, R2S does not oxidize aldehydes. So any aldehydes that are produced, stick. You can also use sometimes zinc and probably zinc and acetic acid is the other set of reagents, I believe. But I'll use R2S. So with ozonolysis, we have a choice. We can keep the aldehydes or we can further oxidize them. So that's what ozone does. And in the book, they'll show you how the ozone, how the three oxygens add to the double bond to make a 5-membered ring. But that doesn't really help us. Because then what happens is we cleave the double bond, so that's just what happens. It forms what's called an ozonide. And this sort of destructive capability of ozone is its bad side, right? Because ozone is good. Way up in the atmosphere where it's keeping the ultraviolet light from the sun from like cooking us alive, that's where the ozone needs to be. Of course, we had that big ozone hole in the 70s because of hairsprays and other things that had the chemicals that went up into the ozone layer and depleted it. And I think there's probably still a hole down in Australia, New Zealand, and Antarctica, but I think it's starting to come back together. It's getting smaller. That was an easy problem to solve because all we had to do was get rid of those chemicals. And there were environmentally friendly alternatives already made. Unlike, global warming where we're trying to make environmentally friendly alternatives to CO2. And that's not as easy. So it's easy to solve the ozone hole problem. It's less easy to solve global warming. So that's what ozone does way up in the atmosphere. Good place for it. If you live in like an urban area, they always have these ozone action days over the summertime when the temperature gets hot, and then they say don't cut your grass, don't fuel your car until after 7. And the reason is because ozone at ground level, bad. Because what does it do? It can attack things with double bonds. So you breathe it in, I'm sure there's a few double bonds in our lungs somewhere. So it has that destructive capability. So that's why ground level ozone is bad. But upper atmosphere ozone is great. So unfortunately we just can't put it in a pipe and shoot it up into the sky. But that's the difference between the ozones. So again, 2 different sets of conditions. Okay. So in the book, they're going to give you a little bit more challenging problems that I probably should have gotten rid of. And they're going to say, okay, they're going to give you like these 2 molecules, and they're going to say, what alkene did this originally come from? And so when you're looking at those molecules, basically everything that is a carbonyl, first of all, you have to kind of work backwards. What reagent did they use? If it's carboxylic acid, then it was originally an H. if they use an oxidizing conditions. Then everything with the CO double bond was attached together. So let me just try and make up an example here. So if they gave you this and said, what alkene was this made from with ozone and H2O2? We would look, and if we see any carboxylic acids, they were originally H's. And then we would say, okay, everything that's a carbonyl was attached together. So that means that the molecule looked something like this. Those two carbons were double bonded to each other. So if there's just one molecule, that means the original molecule is a ring. If there's two molecules, then you just join the carbonyl groups together. Now you say, well, that's not an answer. They didn't write it like this. So now we have to figure out, well, how many carbons are in the ring? And it looks like there is 1, 2, 3, 4, 5 carbons in the ring. So that means I've got a 1, 2, 3, 4, 5 with a double bond in it. And this is where I might number everything. So carbons 1 and 5 are bonded by the double bond, and then 2, 3, and 4 like that. And so what am I missing? I'm missing a methyl group attached to carbon 1. So if I put the structure back together again, this molecule, when you treat it with ozone and hydrogen peroxide, makes that product. So you have to kind of think backwards in this. And it's possible, since this is in that homework set, I might ask you a question like this on the phone. Okay. On 5?
Yeah.
In the end, it doesn't really matter, right? You get the same structure. 5-member ring with the double bond with 1 methyl group on the double bond. Okay? All right, so if you have questions, like I said, email me, come see me. Otherwise, I think you've got plenty of practice problems to work with, and you can go from there. All right? So at the latest, I will see you next Friday.